Hello, this is the first video on chapter 16 on waves. Chapter 16 is on traveling waves, and then chapter 17 is also on waves, but standing waves. So chapter 7, basically this chapter is some of the basics of waves, and then chapter 17 we combine waves in certain ways. So we'll hold off on that until after quiz 1. So the main thing I want to get to in this video is what's the difference between these kinds of graphs. So you're going to do a lot of graphical analysis in this chapter, and so you're going to see a graph, and you're going to see a lot of wavy graphs, sines and cosines, so the graph in red is very, very different from the graph in blue, and we want to be able to describe what each is. Each one is telling us sort of a story, so we want to be able to describe both of those separately, and then combine the two facts as well. Okay, so first of all, what is a wave? I don't like this page in the book for two reasons. One is they call this a surfer when it's obviously a boogie boarder. But the more important one is what is a wave? They say a wave is a disturbance traveling through a medium. So everyone counts E&M waves as well, and E&M waves don't require a medium, so that's already not entirely true. So how would we define a wave? I would say that a wave is a disturbance that the overall effect of the disturbance is to transport energy across long distances without the net transport of matter. Okay, so you'll notice in both of these examples, like for a wave on a string, so you flick a jump rope or something, and that wave pulse is traveling to the right. Any one piece of the rope temporarily goes up and then back to its resting position. It doesn't really travel a long distance, but the whole pulse, which is carrying energy, is traveling over a long distance. So that's true for that example. It's true for, it looks like you have a compression in the spring that's propagating through. So that's common to all of these waves. Okay. So we're going to be talking about a lot of different types of waves throughout the chapters. And so I just want to give you a way of organizing them in your mind. So first of all, we can separate waves into transverse waves and longitudinal waves. So really all waves, so there exist waves that have properties of both of these two things. There are both transverse and longitudinal. So like, for example, this picture of the surfer, water waves have transverse and longitudinal parts to them. But they tend to be, more complicated to describe mathematically. So at least for the chapters in this book, they tend to separate the chapters and the types of waves into these two pieces. So what's the difference between these two? So you got a sense right here from the jump rope. So any one piece of the jump rope is moving up and down in a direction that's perpendicular to the direction the wave is traveling. So see how the wave pulse is traveling to the right. But if you focus on any little piece of the jump rope, it just moves up and then back down. So this is to be contrasted with the longitudinal wave where the spring is bouncing back and forth left and right, and then the transport of energy is traveling to the right. So that's along the same direction. There's another picture of it, and I would pause and check out the simulation. So I'll post a link to a simulation to help you visualize this over time. So check that out in the video description. Okay, so the main example of longitudinal waves are sound waves. We're going to be focusing on aspects of sound later in this chapter and in the next chapter. But sound, the way sound arrives to your ear, so whatever the speaker is creating oscillations in the air that are just sort of bouncing back and forth. So it's propagating kind of like this slinky right here. So these bouncings, imagine that these compressions and expansions of the spring are just going off to the right. So the air molecules are actually doing this sort of bouncing thing by the time they get to your ear, and that's how you can hear things. So it requires obviously air particles, and that's why there's no sound in space. So there's three main waves that we're going to look at. The sound is the only longitudinal one. For transverse, we have two main examples. So one is going to be waves on strings. So like this jump rope example right here. And then another one is E&M waves. So here the disturbance, so like I said before, this doesn't require any matter. So waves on strings and sound waves, these are actual particles moving. E&M waves, the disturbance, and this is why they use this word disturbance rather than a particle, because they want it to be a little bit more general. E&M waves, the disturbance is an electric field and a magnetic field. And that disturbance is in a direction that's perpendicular to the direction that the wave is traveling. So you have light, you turn on a light switch, look at the light's traveling from the light bulb to your eyeball. Along that path, though, there's an electric field that's going perpendicular to that direction. And there's a magnetic field perpendicular to that direction as well. So we'll look at those waves mathematically way down the line. So this will be after thermodynamics in like week 6 or 7 or so. But we will talk about some properties that are common to all of these things. Wave speed, we're going to save for next video, where I'll talk about wave speed of all three of these things separately. So we'll hold off on that. So really, I want to start to get at answering this question. So the difference between these two graphs. Probably the more, the one that you're used to, or the one that makes a little bit more sense, is this blue one right here. So we're going to start with this one right here. So let me go ahead and draw. So I'm going to draw something that's supposed to symbolize basically this wave pulse that's traveling down. So it kind of looks like a spring here, but we really want to think of this wave on the left as a wave on a string. Whoa, super zoomed in. Why is that? Well, the disturbance is going up and down, right? Any one piece of that even though it looks like a slinky or something, the disturbance is traveling up and down, even though the wave is traveling to the right. So that's going to be a transverse wave, not a longitudinal wave. Okay, so the picture of that. So I'm going to try and stick with blue to represent this kind of graph, and then red for the other kind. Okay, so a snapshot graph is a graph describing the displacement. So sometimes you'll see y as a function of x and t, but in more generality, we use capital D. So the capital D is used so that we could be describing either a transverse wave or a longitudinal wave. So in this case, you could think of, for a transverse wave, for this picture, you can think of this as y, the y coordinate. So displacement as a function of x. And then what's special about a snapshot graph is that we're holding t constant in time. So you might see it written like this: d as a function of x comma t naught, where the naught is symbolizing that it's some constant, or t equals t naught to make it even more explicit. That part is constant. So why is this called a snapshot? It's just like taking a picture. I mean, you're seeing 4 of them right here. You're seeing 4 different pictures. So you're seeing 4 different snapshot graphs at different times. And assuming that the earlier pictures were taken at the top and then the later ones at the bottom, it looks like this wave pulse is traveling to the right. Okay. So a snapshot is literally just writing down, it's a graph that's showing a picture of the wave. So this is d as a function of x. So for a particular moment in time, let's say that the wave looks like this. So let's say that this is at t equals 0. This is what the wave pulse looks like. So this is saying where the height is. So capital D is the height, or the y value, where the height is of the rope as a function of where we are along the x-axis. So if this wave is traveling to the right, we can, it'll look something like this some amount of time later. So a snapshot graph only has one of these. I'm sort of drawing 2 on top of each other, but normally you just see one on these axes. So this is at some later time. So we'll call this t equals 1 second. It's hard to write in dotted line. Okay, so let's just to talk about some numbers here. Let's say that that's 2, 3, 4, let's write these out a little more. 5, 6, etc. So I have in mind that this peak lines up right here, and this peak lines up right here. Okay, so this will be 1 meter, 2 meters, 3 meters, 4 meters, 5 meters, 6 meters. So in general, if you have a snapshot graph, you don't know the speed of the wave. However, if you do have a snapshot graph like this, and you have the graph at 2 different moments in time, we can infer what the wave speed is, right? You can just track the peak of that pulse. So if I look at this point right here, and I just focus on this pulse as it travels to the right, it winds up right here after 1 second. So it looks like the wave speed here. So the speed is, so let me just write down V. So here in this example, V is equal to 2 meters per second. Right? That dot traveled 2 meters in 1 second. Now you want to be careful. This V is the wave speed. This is the speed that the pulse is traveling to the right. That's different than the speed of any piece of the rope, right? Or piece of the string. Remember, any piece of the string is just traveling up and then down. Right? So the particle speed is not the same thing as the wave speed. Right? Okay, now there are other types of graphs that you'll see that tell a different kind of story for the same wave. So we're just going to describe the same wave, except now we're going to describe it in terms of history graphs. I guess just to be consistent with this. History has the displacement as a function of, so this time we're going to hold x constant. X is equal to some constant value. And we're going to track the displacement over time. Okay. So just like we had to pick a t value when we were doing a snapshot graph, in other words, you have to pick a time where you're going to take a picture of the wave, right? That's what this constant is right here. So this is when did I take the picture. I don't want to clutter up the picture too much. Here I have to decide where I want to focus on the particle. So let's just focus on 3 meters. So I'm just going to look at, let's do 4 meters actually. I'm going to focus at 4 meters. So let's just choose, just for the sake of analyzing this problem in detail, let's choose x naught, the constant here, to be equal to 4 meters. Okay. So we're drawing, I'm going to need a little more, oops. I guess to see what's going on up above, I need to make that bigger, right? Okay, so I want to draw, so remember a history graph is D versus T. And we're going to look at this particular location. So so what this graph is doing is it's describing where along the y direction this particle is at x equals 4. So see how, okay, so first focus on the solid blue line. So remember, this is t equals 0. So for t equals 0, x equals 4 meters, the particle isn't quite at y equals 0, or capital D equals 0. It's right here. So that corresponds to this point on this graph, right? T equals 0, and then this whole graph is going to be x equals 4 meters. Okay, and then what about, so let's see. So this was at 0 seconds. And then what about 1 second? Where is that particle at 1 second? Well, looks like it's at the peak of its trajectory, right? So imagine, so this graph, remember, is moving to the right. And as the graph moves to the right, imagine that solid line is just shifted over to the right a little bit. This particle is actually moving upwards. Okay, so this particle is moving upwards, and it looks like it reaches its peak right at that moment at t equals 1 second. If we wait a little bit longer, this wave is going to travel a little bit to the right, and then 4 meters is going to start moving down. That's like this point over here. So these graphs get confusing because it looks like you're drawing the same thing over and over again, but it's saying a completely different story. So this is tracking what that one particle is doing over time. So at t equals 0, it's already started its journey on the way up. If we looked at earlier times, it would be even lower, right? And so imagine that solid line. At earlier times, it was, you know, this pulse was over here, and it was even lower over here. So it looks almost the same, right? It's just a wave pulse. You know, if I just gave you the two graphs, you would say, well, they're the same thing, but they're saying completely different things, right? This red graph is it's tracking where this particle is along the vertical direction, whereas the blue graph is a picture of what's going on with the wave pulse. Right? Okay, so in class we'll do an example of you know, given one of these graphs and a little bit of information, you should be able to draw the other one. So that's exactly what we did, right? We took the snapshot graph and we were able to fill in what the history graph must have looked like. Yeah. Okay, so there are a couple additional things that I want to go over regarding sinusoidal waves. Okay, so so if you keep going on in the book, so what we just did was in this one-dimensional waves, and they provide some nice pictures. I'm trying to visualize what's going on, so you can also take a look there. Longitudinal waves, notice how it's the same graph, except the displacement is along the same direction. So that capital D is now delta x instead of y. But the sort of analysis is the same. It's just the pictures get a little bit harder to visualize. Now for sinusoidal waves, we can, so the reason we're going to focus on this is that sinusoidal waves appear a lot in nature. You know, when you turn on a light switch, you can describe the E&M waves with sines and cosines pretty accurately. Even sound, you know, even if I'm not singing a perfect pitch. So if I sing a note and it's a perfect one frequency, it'll look like a nice sine wave. The way I'm speaking, it's not. You know, it's a combination of a bunch of things, but we can do it as a sum of sine waves. So it's a nice basis of functions to use. Okay, so again, I want to focus on the difference between, and here's where I'm going to need a little bit more room. So I want to focus on the difference between a snapshot graph versus the history graph. Okay, again, it's going to look they're going to look similar because they're both going to be sines and cosines. They're both going to look like sines and cosines. You're going to be sick of sines and cosines if you're not already. Okay, so a snapshot graph is going to look like, so again, we'll have capital D versus, remember snapshot is like a picture, it's versus x. Okay, now the x is kind of arbitrary. We're just saying that the wave is moving in the plus or minus x direction. So some problems you might see y or z on the horizontal. That just means that the wave is traveling in that direction. And then this is either in a perpendicular direction if you have a transverse wave, or the same direction if it's longitudinal. Okay, let's suppose we had a wave that looked like this. For a snapshot graph, there's some information that you can read off of the graph. And that is, so if I track either peak to peak or minimum to minimum, trough to trough, or I could do, you know, where the axis crosses the equilibrium spot, but then I got to be a little careful there because I can't do this point right there, right? It's not exactly, this is where the graph is going up, this is where it's going down. So I'd have to go from there to there. All of these will be one wavelength. So this is the wavelength lambda. So if I had a wave on a string, you know, like a jump rope or something, and I kept, you know, I had a regular up and down motion to where it looked like a sine or a cosine wave, I could describe it's the distance between, from one peak to the next peak is the wavelength. So we have wavelength lambda. Another thing that's going to be more useful though, when we describe these waves mathematically, is something called wave number. Okay, so later on in this section, when your book does a little bit more math, they introduce this other thing, wave number, k. And this k, once you know one of these two things, you know the other one. So k is 2 pi over lambda. If you know what lambda is, you know what k is. So wavelength is a distance. The SI units will be in meters. Wave number are inverse meters. And it looks like with the 2 pi, you can infer that it's radians per meter. So what that means is if I took a meter stick and I put it on top of my wave, how many radians of oscillations are there? So I'm probably going to erase this, but so for example, pretend this is 1 meter from here to here. It looks like we do 1 oscillation in that distance, 2 oscillations in that distance. So 2 oscillations would be 4 pi radians in that 1 meter. So the wave number would be 4 pi radians per meter. And then once you knew the wave number, you could get the wavelength. So it's saying the same information though. Once you know one of those two things, you know the other one. Now in a history graph, you get different information from the graph. So a history graph for a sinusoidal function is going to be, it's going to look similar. So by the way, let's assume that this graph is moving to the right. And let's assume that this history graph, so let's assume that, if I want to, I'm going to base this history graph on the snapshot graph. So I need a little bit of information to do that. So I'm going to say that I'm going to focus on x equals 0 here. And I'm going to say that this graph was drawn at t equals 0 right here. Okay, so if this graph was drawn at t equals 0, then I know at t equals 0 and x equals 0, I have 0. Right? So this graph or this point and this point, the same represent the same point in the same moment in time and position in space, or point in space-time. Okay, so what happens when that, so imagine this solid blue graph moves over to the right a little bit. So this graph is going to, so if I extend it a little bit, this graph looks like that. If it scoots over to the right, it looks like this point moves down. So what that means is if I wait a little bit of time, so at some positive time, this is going to move down. So this graph goes down right there. And it's also going to do its oscillatory motion. So it's still sines and cosines, but see how it looks like it's sort of backwards, right? So in general, if a snapshot graph is moving to the right, the history graph looks kind of backwards. It looks inverted, flipped horizontally. And if the wave is traveling to the left, then they look very similar to each other. Okay, we didn't see this sort of effect right here because it was a symmetrical function. So if you invert horizontally, it just looks the same. Okay, now the type of information you get from a history graph is very different. So if I look from peak to peak, or trough to trough, or whatever, this is going to be the period. This is the amount of time it takes to undergo one full oscillation. So if you remember anything about oscillatory motion in Physics 2a, these are the kinds of graphs that you focused on. You focused on simple harmonic motion, where the displacement as a function of time looked like a sinusoidal function, and the information that you got off the graph was the period. So you can get the period, t. You can talk about the frequency, f, which is 1 over t. Or you could talk about angular frequency, omega, which is 2 pi f. So again, once you know one of these things, you know all of them. Just like, so with wavelength and wave number, once you knew one of them, you knew the other one. Once you know one of these 3 things, you know the other 2. Okay, but if you know something about the wavelength, that doesn't tell you anything about the period. If you only have one of these graphs, you need a little bit more information before filling in the other graph. Okay, so the last thing that we'll do to introduce sort of the next section is how to connect these two. So these two will, the way we connect quantities like wavelength and period is through the wave speed. So this is how quickly the pulse is traveling, to the left or to the right. So the wave speed, v. So maybe, I think a lot of you have seen this from chemistry or something. This is going to be wavelength times frequency, the natural frequency, cycles per second or hertz, and then wavelength. And another way, so we're going to start, when we start writing down these functions, we're going to use k and omega for the most part. Those are the easiest to deal with, in which case the wave speed looks like omega divided by k. Okay, so you might want to double check that you can show, you plug in for lambda in terms of omega, or sorry, lambda in terms of k, and then plug in frequency in terms of omega, and the 2 pi's will cancel out, and you'll get something that looks like this. So finally, so both of these look like a sinusoidal function. We can describe, so this is limited though, right? This whole graph is just describing x equals 0. And this whole graph is just describing t equals 0. If we want to describe the whole wave at all positions and at all times, then we need a function of both x and t. So when you see this mathematically written out, you have something that looks like this: kx, and then either minus or plus omega t plus a phase constant. So if I plug in one of these two things to be a constant, then I can reabsorb that constant with this constant, so it just becomes a constant. And then I either get cosine of kx or I get cosine of omega t. And that's exactly what these two graphs are. This is a cosine kx, and then it could be shifted over to the left or to the right some amount. And this is a cosine omega t, shifted over some amount. But in general, this will describe any wave, any sinusoidal wave that we want. Now, a quick note about the sign here. Let's switch colors here. Quick note about the sign. The minus sign, you choose the minus sign. So there's a relative minus sign between the kx and the omega t if the wave is traveling in the positive x direction. Wave traveling in the positive x direction. And you choose the plus if the wave is traveling in the negative x direction. Okay, so over half the class is just happy knowing that fact. Maybe you can explore why, and we can talk on Piazza about why that is if you're interested. Okay, so next video we'll really explore this equation, the wave speed, and talk about the wave speed for the different kinds of waves that we've introduced.